Welcome to a video on determining the greatest common factor. The greatest common factor, or GCF, also known as the highest common factor or greatest common divisor, of two or more non-zero integers is the largest positive integer that divides the numbers without a remainder. I also want to mention the greatest common denominator when working with fractions is just the greatest common factor of the denominators. Okay, so to determine the GCF of two integers, we're going to use prime factors. And the greatest common factor can be determined by analyzing the prime factorizations of the two numbers. Here's an example. If we want to compute the GCF of 18 and 84, we first find the prime factorizations. So 18 is equal to 2 times 3 times 3, and 84 is equal to 2 times 2 times 3 times 7. Now we'll identify which factors they have in common. Notice 18 and 84 share a common factor of 2, and they also share a common factor of 1, 3. Another way to think of this is that the overlap of these prime factorizations are 2 and 3. Therefore, 2 times 3, which equals 6, is the greatest common factor of 18 and 84. Here's another example. Let's say we want to determine the greatest common divisor, which remember is the same as the greatest common factor, of 48 and 180. The first step would be to write out the prime factorizations of each term as we see here. And the next thing we'll do is identify which prime factors they have in common and how many. So we can see if we look at the factors of 2, this has 4 factors of 2 and this has 2 factors of 2. They have 2 factors of 2 in common. Let's go ahead and highlight those. And notice they also share a factor of 3 in common. So 2 times 2 times 3 is the greatest common factor. That would be 12. Another way to look at this is with a Venn diagram where this represents 48 and this represents 180. And you can see that the overlap, or they share the prime factors of 2 times 2 times 3, which again is equal to 12. Let's go and try a few of our own now. So the first step is to write these terms out in prime factored form. One way to determine the prime factorization is to make a factor tree. 60 is equal to 6 times 10. 6 is equal to 2 times 3, which are both prime. And 10 is equal to 2 times 5, which are both prime factors. So 60 is equal to 2 times 2 times 3 times 5. It is helpful to put these in order from least to greatest. Now let's take a look at 72. Start off with two numbers whose product is 72. How about 9 times 8? Well, 9 is 3 times 3, which are both prime. 8 would be 4 times 2. 2 is prime. And 4 is 2 times 2. So we have 3 factors of 2 and 2 factors of 3. Now we'll identify the prime factors in common. Notice this has 2 factors of 2, this has 3 factors of 2, so they have 2 factors of 2 in common. They also have 1 factor of 3 in common. So this overlap of prime factors represents the GCF. The GCF is equal to 2 times 2 times 3, which is equal to 12. Let's go ahead and try another one. So notice now we're introducing variables, but the procedure is going to be exactly the same. Let's go ahead and write these out in prime factored form. 27 would be 3 times 3 times 3. X squared would be 2 factors of x. Y squared is 2 factors of y. Now we'll do the same with 15. X cubed y. 15 is 3 times 5. X cubed would be 3 factors of x and 1 factor of y. Again, we'll circle the factors they have in common. So they have 1 factor of 3 in common, no factors of 5 in common, but they do have factors of x in common. In fact, they have 2 factors of x in common and 1 factor of y in common. So whatever we end up circling, or wherever they overlap, that represents the GCF. So the GCF is equal to 3 times 2 factors of x times 1 factor of y, which is equal to 3x squared y. Let's go ahead and try another. So again, it's going to be the same procedure each time. It's just that as these coefficients become larger, it may take some more time to find the prime factorization. Let's take a look at 120. That would be 12 times 10, 4 times 3, 3 is prime, 4 is 2 times 2, and 10 is 2 times 5. Okay, so the prime factorization of 120 would be 3 factors of 2, 1 factor of 3, and 1 factor of 5. We have 5 factors of m and 2 factors of n. We found the prime factorization of 72 on the previous screen. Let's go ahead and show it again though. Be 8 times 9, 4 times 2, 2 times 2. So we have 3 factors of 2 and 2 factors of 3. Next we have 2 factors of m and 4 factors of n. Let's go ahead and identify where they overlap or what factors they have in common. Notice they have 3 factors of 2 in common, 1 factor of 3, 2 factors of m, and looks like 2 factors of n. So again, whenever we end up circling represents the greatest common factor. So our greatest common factor is equal to 2 times 2 times 2 times 3. That's 24 m squared n squared. Now one thing I do want to point out, notice that if you take a look at the variable parts of the terms, the least exponent on m is 2, and the least exponent on n is also 2, and those are the exponents on the factors of m and n in the GCF. Let's go ahead and try one more. Now notice we have 2 trinomials, and we want to determine the GCF again. Well, the procedure is the same. We're going to write these out in factored form, and then identify where their factors overlap or what factors they have in common. So we'll go ahead and factor these. If you haven't covered factoring trinomials yet in your course, you can go ahead and just skip this example. But the procedure is exactly the same. We want to determine the factors of -6 that add to -1. That would be a -3 and a +1. Now we want to find the factors of +3 that add to -4. That would be a -3 and a -1. This trinomial has 2 factors. This trinomial has 2 factors. The only factor they have in common is the factor of x minus 3. So the GCF of these 2 trinomials is the factor of x minus 3. One of the things that's very common is to get confused between the greatest common factor and the least common multiple. So you may want to watch the video on least common multiple next if you haven't already. Thank you for watching.